Okay, the last talk of the session is on theoretical linear cryptanalysis of the 5G standard candidate SNO 5G, and it's by Liu, Yin Yang, Tian Tiang, and welcome back on stage, Liu.
Thanks for the introduction. Hello, everyone. I'm Liu. Today, I will present our work, Theoretical Cryptanalysis of the 5G standard candidate SNO 5G. This is our joint work with Jin Yang and Tian Tian. Our talk is divided into 4 parts: motivation, the SNO 5G cipher, theoretical linear cryptanalysis of SNO 5G, and conclusions. Initially, I introduced our motivation. SNO 5G is a 5G standard candidate stream cipher originating from SNOW and SNOWI, providing 256-bit security. SNOW and SNOWI are capable of achieving rates of up to 58 Gbps and 92 Gbps. SNOWI series has received much public evaluations, including gas and determinant attacks, linear cryptanalysis, integral attack, differential attack, and so on. The main challenge in linear cryptanalysis stems from the large states of these ciphers. This often obstructs automatic search tools from finding the optimal linear masks. Differing from conventional methods, our work relies on the theoretical cryptanalysis. Based on the theoretical linear cryptanalysis, we derive the relationships among linear masks. Furthermore, we propose a divide and conquer method to shrink the linear mask space. This enables us to filter out linear trios with decent correlations without relying on automatic search tools. By this way, we can search for linear trios in a restricted space. Next, I will give a brief introduction to the SNO 5G cipher. The SNO 5G cipher is composed of a linear part and a nonlinear part. The linear part contains 2 linear feedback registers, and the nonlinear part is a finite state machine. The linear part is built over 2 LFSRs, called LFSR-A and LFSR-B, each with 16 stages and 512 bits in total. The stages of LFSRs are generated by the 2 polynomials respectively. Subsequently, 2 128-bit types T1 and T2 are extracted and fed to the FSM. The FSM part includes 3 128-bit registers R1, R2, R3, and takes T1 and T2 from the LFSRs to produce a 128-bit keystream word and update the registers. These registers are updated by the AS round function, 16-bit modular addition, exclusive OR, and permutation sigma. Then I will introduce our main work, theoretical linear cryptanalysis of SNO 5G. We consider the keystream outputs in 3 consecutive clocks, T-1, T+1. We apply 3 128-bit linear masks, alpha, beta, and gamma, to ZT+1, ZT, and ZT+1, respectively, and introduce L, M, N, and H to the LFSR outputs to obtain the linear approximation N. Subsequent analysis is based on this linear approximation. We introduce intermediate linear mask C and partition the linear approximation N into 3 parts, N1, N2, and N3. We observe that the approximation N1 is independent of the N2 and N3. Therefore, we only needed to exhaust the immediate mask C to compute the correlation of the linear approximation by this equation. The linear approximation have two nonlinear components, a S-round function and a 16-bit modular addition. We divide the linear approximation into small linear approximations of three types. For initial filtering, further division of linear approximation makes it easier to observe the relationships among linear masks. And we further divide the N2 into two independent parts, P1 and P2. And the correlation of N2 is a product of P1 and P2. We introduce two intermediate masks Z1 and Z2 to achieve a more detailed segmentation. These masks enable us to split N1 into two pairs, M1 and M2, and P2 into M3 and M4. The two pairs have an AES-round function and a 16-bit modular addition. Next, we introduce an intermediate mask theta and divide N3 into P3 and P4. The linear mask sigma theta in P4 indicates the permutation sigma acts on the theta. After the further division of linear cryptanalysis, we classify the linear approximations into three types, type 1, type 2, and type 3. And we discuss the nonlinear operations in three types, linear approximations. Type 1 only utilizes the AES encryption round function. Type 2 only involves 16 modular addition. And type 3 is a combination of the two. For the type 1 linear approximation, the metric is the number of active S boxes with AES round function. As for the type 2 linear approximation, the metric is the number of active 16-bit modular addition blocks. When it comes to type 3 approximation, its metric is a combination of the metrics of type 1 and type 2. The divide and conquer method can be implemented through the following structured steps. First, we partition linear masks into 5 cases based on a critical intermediate mask. And we apply two metrics, the number of active S boxes and 16-bit modular addition blocks to initially filter the linear approximation. And we obtain the optimal templates to shrink the linear mask space. Finally, we perform the in-depth filter using correlations. Here we introduce the details of the divide and conquer method. We firstly concentrate on the essential filtering. But before we perform essential filtering, we focus on the critical linear approximation and its mask zeta. Zeta affects the linear masks gamma, N, beta, C, and H through 16-bit modular addition. Moreover, it further affects other masks where these masks across 16-bit modular addition and the AES round function. So we classify all linear masks into 5 cases according to the number of active bits in theta. For each case, we calculate the matrix and record the optimal value. Then we get 2 descent templates. And these metrics are presented in this table. It can be seen that the positions of the active bits of zeta are fixed. Yet, beta is determined when the number of zeta is true and undetermined when it is 4. Moreover, we can effectively narrow the space of others based on the constraints among linear masks. We now concentrate on the further filtering phase, which aims to identify optimal linear masks based on these precise correlations. In this step, we compute the optimal correlations for each template and compare them to determine the ultimate optimum. When the number of theta is true, we obtain the optimal result with a correlation of negative 2 to the power of negative 67.67. It can be seen that we use the product of the correlations of N1, N2, and N3 to approximate the correlation of N. Additionally, it is necessary to verify that the chosen Xi is the dominant one. For specific, we should rank the candidates of Xi to 2 power of 16 values. Moreover, we further compute the correlation of suboptimal linear trio having the same outer masks, and the value is 2 to the power of negative 74.38. In conclusion, we see there is no requirement to consider the linear Hall effect. In the end, we launched a correlation talk against the SNO 5G, and the total time data and memory complexities are shown in this table. Our method improves the existing benchmark 2 to the power of negative 75.82 by 2 to the power of 8.15. At last, I gave a conclusion to this talk. Overall, through theoretical cryptanalysis, we initially analyze the properties of the nonlinear components. Then we acquire the templates of linear masks. After that, we compute the matrix for various cases. Eventually, we get 2 candidates for the templates. Using these templates, we further compute the correlations, compare them, and determine the optimal one. We perform the analysis from the theoretical point of view. Based on the theoretical cryptanalysis, our method not only provides a better understanding of SNO 5G, but also does not rely on automatic search tools or linear approximation tables. Our approach involves minimal computation due to the 2 filtering phases. Thanks for your attention.
Okay, we have time for questions. So are there any questions? Okay, maybe I have a question. So if you go back one slide, please. I have a question. So go back one slide back. Yes, you said you did not use any automatic search or something like this to provide your approximations. What do you think? Is it possible to adjust this search tools to have such a similar to perform as similar as you with the theoretical result?
I think that it is. I think you are right. I think our method can implemented to other cases because its main idea is divide and conquer method. It aims to solve the stream cipher with large states.
Okay, thank you. So any other questions arise now? Okay, so every session has come to an end, so does this as well. So let's thank all the speakers of the session again. Thanks, it's been a great audience.